real number. All right, so that means, okay, after the evaluation of the dot product, it will return us with a real number. All right, one important thing, okay, for the dot product. All right, so this is the definition 8. Okay, I would like to recap. Okay, and now you may ask, okay, hey Patrick, seems that, okay, this is only for two-dimensional, right? Okay, R2 space, or the vector consists of two components. Okay, how about n-dimensional space? Okay, and can the dot products be applicable? Okay, or still be applied, okay, in the area of Rn space? The answer is yes, okay, for sure. We are going to extend or to generalize the result, okay, to an Rn space, a more general space, a vector space. Okay, and then we would like to capture the dot product as follows. So let's go to the definition 9. Similarly, we consider two vectors, vector v and vector w. Actually, the setting, okay, is quite similar. Okay, vector v, vector w, right? Okay, and then yeah, of course, there are different components when we compare with the definition 8. Okay, but in Rn space, you should expect that there are n components. Okay, for the Rn space. Okay, for you. Okay, to reference. Okay, so for vector v and vector w, okay, they are having n components inside the vector. Okay, so again, we can say that, okay, these vectors are in Rn space, and then we would like to explore the dot product of the two vectors, okay, vector v and vector w. So symbolically, okay, we also use a similar notation, v dot w for the dot product. Okay, and then you can also see, again, you are going to operate, okay, the component, the dot product, okay, component wise. So I don't connect that for you because n components, you can see many errors over there. Okay, but I hope you can extend from definition 8, okay, and then to come up with the conclusion, okay, for this definition. Okay, so okay, so this is the generalization of the dot product, and do remember, okay, no matter what kind of dimension we are talking about, do remember, okay, the result or after evaluation. Okay, after the evaluation, okay, you will get a real number. Okay, so after the dot product, do remember you get a real number. Okay, so this is definition 9. Okay, the generalization of the dot product. Okay, now it is time to move to the idea about orthogonal. Okay, what is meant by, okay, two vectors to be orthogonal to each other? Actually, you should have some background about this, okay? Or in some other course, I don't know. You may have already learned that before. So when it comes to orthogonal, okay, of two vectors, okay? So these two vectors, the dot product of these two vectors, okay, suppose v and w of concern, okay, or of interest. I would like to see whether they are, or they can be claimed to be orthogonal if, okay, if the following condition satisfied, which is the dot product of these two vectors, okay, equals 0. Okay, equals 0. In other words, that means v dot w equals 0. But here, okay, do remember 0 is a real number instead of 0 vector or a vector. Okay, so pay attention to this, okay, and the expression. Okay, so let me briefly write down the summary for this definition. It means that if we want to claim or if we want to verify whether or not two vectors are orthogonal to each other, okay, it suffices to check the dot product. It suffices to check the dot product. Okay, I'm not going to use. Okay. Okay, let me repeat. If we want to check whether or not, okay, the given vector are orthogonal to each other, okay, we simply check the dot product equals 0 or not. All right. So this is the idea. Okay, for the orthogonality, okay, or orthogonal, okay, in terms of the vectors, the two vectors of concern. Okay, so this is the idea. So far so good. All right, so let's move on. Okay, we will build on this concept. Okay, in terms of orthogonal. Okay, and then we are going to extend. Okay, instead of not restricted to two vectors. Okay, now I would like to proceed. Okay, to describe the orthogonality in a set. Okay, and even a basis. Okay, so now I would like to borrow this kind of idea, extend to set and basis. So let's take a look. Okay, definition 11. All right, so you can call a set of vector to be a orthogonal set, so-called orthogonal set, if any two distinct vectors in that set are orthogonal. Okay, so let me repeat. If you want to say, or you want to claim a set of vectors in Rn space to be orthogonal set, okay, you are going to check any two distinct vectors, and then in that set, okay, you are going to check the orthogonality, okay, orthogonality. Okay, sorry for that. Okay, for this set, in order to claim the set of vector to be orthogonal set. All right. Okay, so this is the first thing in the definition 11. Okay, and then I also want to build from this idea of orthogonal set. So on the other hand, I can also claim a set to be, or a basis to be orthogonal basis for the general Rn space is an what is the idea? Okay, it consists of two parts. Okay, orthogonal basis is an orthogonal set which is also a basis for the Rn space. Okay, so in order to claim, or in order to find an orthogonal basis, we need to find two things. So firstly, whether or not the set of vector of concern is a orthogonal set or not. Okay. Secondly, whether or not this is a basis for the general Rn space. Okay, so two conditions. Okay, first one, orthogonal set. Secondly, basis for Rn space. If these two conditions are satisfied at the same time, we can claim the concerned set of vector to be orthogonal basis for the Rn space. All right, so this is the idea for the definition 11. Okay, so now I would like to move to the next example. Okay, example 9. Okay, in this example, there is a set. Okay, there is a set. Okay, consists of three vectors. Okay, in a R6 space. Okay, so naturally you should expect there are, for each vector, it consists of 6 elements inside the vector, right? Okay, so-called 6-dimensional space. Okay, interesting, right? And then in this question, you are asked to verify, the set is an orthogonal set. Okay, let me repeat. You are asked to verify whether or not the following set consists of 3 vectors is an orthogonal set. Okay, so we may want to take a look definition 11 as well. In the definition, it tells us that if any two distinct vectors in that set are orthogonal to each other, so we can simply claim the set to be an orthogonal set. In other words, we are going to check quite a number of dot products, right? We are going to check with any two distinct vector and check the dot product in that set. And if the dot product can be verified to be orthogonal, for the any two distinct vector, so we can claim the set to be orthogonal set. All right, so I hope you guys maybe I just kickstart for the first subpart, and then I will leave you some time to go over the remaining tasks as a classwork. Firstly, I would like to pick 2 vectors. Maybe I pick a 1 1 1 1 1 dot another vector. Maybe I pick the second one to be 2 -2 2 -2 2 -2. So after the evaluation for the dot product, what you get? You should get 2 minus 2 plus 2 minus 2 plus 2 minus 2. So you can see and you can check, okay, it equals 0. Okay, do remember, let me repeat. Okay, this is a real number 0. Okay, because the dot product, okay, will produce us with real number. Okay, that's just a reminder. Okay, so I will repeat myself until you can memorize it. Okay, or you can find it easily to understand. Okay, so now, guys, okay, I would like you to take several minutes, okay, to work out the remaining dot product. But by the way, okay, I just want to give you some further information. Okay, suppose now in this set you are having 3 vectors, right? So can you tell me how many number of combination or how many dot products, okay, you are going to work with? Any idea? 3 vectors, and then you are going to pick 2, okay, for the consideration and for the analysis. Okay, so you will get 3. Very good. Very good. Well done. So in general, suppose there are n vectors. Okay, so you are going to pick, okay, NC2 number of combination, okay, to consider. Okay. Of course, the higher the number of n, the higher number of combination, okay, you need to check with. Okay, okay. So just for your reference, okay, I know you guys, okay, should be quite familiar with this. Okay, so maybe how about 5 minutes? Okay, 5 minutes. Okay, to work out the remaining dot product. Okay, and then tell me the conclusion. Tell me your conclusion. Okay, 5 minutes. Okay, I will check the answer with you around 4:50. All right, guys. Any conclusion? Any conclusion? Okay. 0. Okay. What do you mean? Okay, so by the way, let me write down the possible combination of two distinct vectors with you. So another possible combination. So after evaluation, okay, for the dot product, okay, it gives you 0. All right. Of course, you can check. Okay, you can check, but I don't think this is a difficult task for you. Okay, so I leave the intermediate step for you guys. I just want to show you, okay, do remember to include all of the possible combination, okay, inside the checking. Okay, so you can see, chop it into several parts. So you can see in total, there are 3 combinations, okay, 3 combinations, okay, to describe the dot product, okay, to describe the 2 products of any 2 distinct vector. Okay, so based on this observation, you can see that all of the dot product, okay, in the set, they are all equal to 0. Okay, so we can claim that, or we agree. Okay, actually, okay, this conclusion is right. Okay, it is an orthogonal set. All right, it is an orthogonal set. Well done, guys. Okay, so this is not difficult, right? Okay. Okay, so now I would like to, okay, move on, okay, from this. Okay, now I would like to consider, okay, a particular basis. I would like to consider a particular basis, which is called standard basis. Okay, standard basis, actually, you know the actual meaning, right? Okay, in the last subsection, okay, around the end of the subsection about basis. Okay, actually, you can also consider, okay, obviously, okay, actually, it is also a orthogonal basis. Okay, for orthogonal basis, do remember you need to check 2 things: orthogonal set as well as a basis for the general Rn space, and you can see that actually standard basis, okay, is actually fall into these 2 categories. Okay, they are orthogonal to each other. Okay, you can check. And also, as the name suggests, this is already a basis for the Rn space. Okay, so combine these 2 observations, we can see that, okay, this is also an orthogonal basis. All right? All right, okay, so this is just a particular observation, okay, by using the ideas standard basis. Okay, now I would like to move to the theorem 4. Okay, of course, this is the okay, the previous discussion is a building block, okay, for the following discussion, okay, the theorems. Okay, so suppose there is a capital S set, okay, there's a set, capital S, consists of k vectors, okay, okay, and I would like to assume, okay, this set, capital S, is an orthogonal set, okay, of, please be careful here, non-zero vectors in Rn space. All right. So let me repeat. Okay. Now I would like to assume there is a set, capital S, with k number of vectors inside, v1, v2 until the last guy, vk. Okay. So that, okay, this set, okay, will be claimed to be a orthogonal set of non-zero vectors. Okay, okay, in Rn space. Okay, and then for this set, capital S, it is a linearly independent set. Okay, linearly independent set. All right, so please pay attention. Okay, for the theorem. Okay, so we will move to, okay, based on this theorem, okay, we are also developing another interesting but related theorem. Okay, but before that, okay, let me recall a fact to you. Okay, we know that, okay, any set of n linearly independent vectors, okay, in the Rn space, okay, will form a basis for the Rn space. All right. Okay, so this is a fact we already know. It is already known and discussed in the subsection of the basis, right? For Rn space, if we can find n linearly independent vectors, okay, so this set, okay, will be enough to be called a basis for the Rn space, right? And now, okay, I would like to borrow, okay, this idea, okay, and then some terminology before, okay, to form the next theorem 5. Okay, so theorem 5 tells us that any orthogonal set of n non-zero vectors, okay, is an orthogonal basis. Okay. So this is the idea of theorem 5. Okay, so let me repeat. Any orthogonal set of n non-zero vectors, okay, in a general Rn space will be an orthogonal basis, okay, for the Rn space. All right. So this is the idea of theorem 5. Okay, but how we are going to use it? How can we use it? Okay, so let's take a look. Okay, so pay attention to this. Okay, we will see. By the way, okay, let me give you further information. Okay, for the theorem 5 first. Okay, so actually we can develop, okay, we can connect, okay, from theorem 4. Why can I say so? Okay, since, okay, theorem 4, okay, told us a result. Okay, let me see. Okay, let's show it at the same time. Okay. All right. Okay. Theorem 4 tells us that, okay, S is an orthogonal set of some non-zero vectors, right? Okay, and then the set will be so-called linearly independent. Okay, and then we know that any linearly independent vector in Rn space, it can form a basis, right? Okay, so actually, theorem 4 together with, okay, the statement here, okay, actually it leads to the idea of theorem 5, right? So simply write down the connection here. Okay, so orthogonal set. So you can recall that it is linearly independent. And then linearly independent vector in Rn space, okay, form a basis. Okay, form a basis of Rn. All right. Okay, so combine this circle result. Okay, we lead to the next theorem, theorem 5. So any orthogonal set, okay, of n non-zero vectors in Rn space is an orthogonal basis, okay, for the Rn space. All right. So this is the idea. Okay, and the way of thinking, okay, for the theorem 5. All right, and now, okay, I would like to make use of a simple example. Okay, the next example 10. Okay, to develop, okay, some finding, okay, or some result, okay, based on what we have discussed. All right, so example 10. Now, I would like to ask you guys to show the following set of vectors. Okay, in the set, it consists of 4 vectors. Okay, right? 4 vectors. Okay, and then I would like you guys to show the following set of vectors is an so-called orthogonal basis. Okay, so you will have several things to derive. Okay, you will, okay, I will give you guys some times. Okay, so try to work it out. Okay, and then after several minutes, okay, I will come back and discuss with you. Okay, so let me tell you, okay, in order to tackle this problem, okay, of course, okay, I give you the starting point, okay, so you can start easier. Okay, to tackle this question, okay, so we are going to deal with the dot product, okay, the dot products of each pair of vectors, okay, consider this in that set, all right, in that set. Okay, so can you tell me how many number of combinations you expect to work on? There is 4 vectors, and then we are going to pick 2 vectors, right? We are going to pick 2 vectors out of 4 vectors. So we are going to have, okay, 6 combinations. Okay, we are going to have 6 combinations, okay, to work with. Okay, and okay, I hope you guys will have some time, okay, spend some time, okay, to verify the dot product for me, okay, and then try to link, okay, the last theorem, okay, last several theorems, of course, okay, 4 and 5, theorem 4 and 5, okay, and make the conclusion for me. whether or not, okay, the vector can form, okay, can form an orthogonal basis. Okay, so I give you guys 10 minutes. Okay, let's see whether it is enough or not. Okay, I will ask you, okay, in case you are out of time or in case you need more. Okay, so 10 minutes. Okay, and then I will discuss the suggested answer around 5:10. Okay. Hey guys, is all right? Okay, successfully check all of the combination. Yeah, some of you tell me are talking to each other. Okay, most of you say they are talking to each other. All right, not bad. So let's take a look. Okay, let's take a look. Okay, so of course I just work out one initial or starting example. Okay, so the rest of them, okay, you can use a similar idea. Okay, to verify. I just pick the maybe the first vector in the set. Okay, and the second one. Okay, so you can see when you break the dot product, you get -1 plus 0 plus 1 plus 0. Okay, so for the combination, the first and the second vector, the dot product will be 0. Of course, you are going to have some other combination. Okay, but the intermediate steps, okay, I just skip it. Okay, and then just tell you the answer. Okay, so when you consider the following set of combination, okay, so you will get and you will see the dot product, okay, will all yield to be 0. Okay, and then based on this observation, okay, we can claim that okay, the vector in the set, okay, clearly are orthogonal to each other. Okay. Okay, because we check all of the combination, right? So we can, or we are safe, okay, to claim, okay, the set of course, it consists of many vectors, are orthogonal to each other. Okay, the vectors in this set are orthogonal to each other, and then by using theorem 5, okay, by theorem 5, okay, so the vectors in the set, okay, form an orthogonal basis. Okay, form an orthogonal basis. All right. Okay. Of course, for the output space. Okay. So some intermediate steps. Okay, I hope you guys can carry out for me later. Okay, at home. Okay, later today. So in this example, okay, I just want to tell you or illustrate the idea. Okay, how to verify for an orthogonal basis. Okay, what kind of steps or what kind of so how many, for example, how many number of combinations you need to consider, and then based on the results you have, okay, for example, in black, okay, so you can infer, okay, or it implies, okay, some new findings, okay, and then what kind of conclusion you can draw, okay. So I hope you can develop such kind of sense. All right. Okay, so now I would like to build on this kind of idea. Okay, and then I would like to ask you one more question. Okay, Okay, suppose that. Okay, you are given a orthogonal basis. Okay, for example, okay, based on the question, okay, it is nice. Okay, to tell you, okay, the given set is an orthogonal basis. Okay, and now, okay, we know that every vector, okay, should be able to express in terms of the vector in that basis, right? Okay, now, okay, I would like to ask, are there any ways, okay, are there any theorem, okay, so that I can follow to form so-called linear combination, okay, for a random vector in that particular vector space? Okay, so this is the next question, okay, I would like to address. Okay, so let's move to the page 25. All right. Lastly, we developed the idea for the orthogonal basis. And now, suppose you are given an orthogonal basis, okay? Orthogonal basis, okay, for the general Rn space, okay? This is given, right? And then now, I would like to ask whether or not it is easy or is it possible, okay, to write any given vector, okay, as a linear combination of the basis vector in that set, okay, in that set. And let me tell you, it is super easy, okay, to write down the given vector to be a linear combination of the basis vector. And in particular, we are using dot product, okay, to illustrate how we are going to achieve this result. Okay, so let's take a look at the next theorem. Okay, so when we finish this theorem and the next example, we will take a break. Okay. All right. Let's go to the theorem 6. Okay, so firstly, assume there is an orthogonal basis, okay, for the Rn space. Based on the idea, we know that these spaces consist of n vectors, namely v1, v2, blah 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 until last guy vn. Okay, so the whole set consists of n vectors is an orthogonal basis, okay, for Rn space. And now I also assume there is a random vector, okay, random vector u, okay. So this is any vector inside the n-dimensional space. Vector u is an any vector, okay. And actually, the vector u can be expressed as follows. Can be expressed in terms of the vectors in the inside the orthogonal basis. Okay, so you can see, okay, there is a very big or very long expression. Okay, but when you take a closer look at, actually it follows some pattern. All right, and then you can also, I believe, okay, you should be able to verify, okay, whether or not this is orthogonal to each other or any interesting property, okay, you can find. Okay, but here, I just want to remind you something. Okay, Firstly, okay, I keep mentioning that. What is the final product or resultant product after dot product? Okay, dot product will return us with real number, right? Right. Very good. Okay, so in the expression, you can see quite a number of dot products over there, right? Okay, so this guy, okay, dot product. This guy, dot product. Okay, I don't explicitly discuss the other one. Okay, because we can extend, okay, the result one by one. I just want to focus on the first item, okay, on the right hand side of the equal sign. So you can see in the fraction, the numerator as well as the denominator, they are dot product. In other words, we are having real number divided by real number, right? So can you tell me, okay, for the fraction, okay, real number divided by real number, what is the nature of this kind of, for this fraction? Okay, I just want to ask you. Real number divided by real number. Of course, you are going to get a real number, right? Okay, so this is the first finding. Secondly, I want to ask you, would you need to worry about the denominator to be 0? Would you need, okay, let me repeat my question. Would you need to worry about, okay, the denominator to be 0? In other words, that means v1.v1 or v2.v2 until the last guy vn.vn. Do you need to worry about the dot product to be 0? Because, okay, some number, real number, right, divided by 0. Of course, it will be undivided or it will be problematic, right? But, okay, let me ask you a question. Do we need to worry about this situation? Any idea? Do we need to? Very good. Guys, okay, I see quite a number of you respond correctly. So let me go back to the previous page a bit. Okay, so let's go back to the theorem 5. Initially, in the theorem 5, we assume, okay, there is a orthogonal set, right? Okay, of n non-zero vector. Okay, so I use another color. Okay, maybe I use highlight pen. Okay, maybe sky. Okay, we consider n non-zero vector in order to construct the so-called orthogonal basis. Okay, so inside the orthogonal basis, based on the theorem 5, none of them is zero vector. All right, so you don't need to. Okay, so okay, we just using theorem 5. Okay, to develop some observation. Okay, to develop some finding. Okay, some finding. Okay, for the theorem 6. So you can see, okay, theorem 5, theorem 4 develop theorem 5, theorem 5 of course develop theorem 6. All right. Okay, so get back to the theorem 6, and I would like to confirm you. Firstly, okay, dot product return us with real number. Okay, so for each item or each quantity, you can see there is a fraction, right? A fraction consists of two dot product, okay, in the numerator and the denominator. So it implies that, okay, real number divided by the real number. Of course, okay, inside the bracket, inside each bracket, it will return us with real number. Okay, so this is the first thing. Secondly, okay, I would like to ask you, okay, do we need to worry about the bracket, inside the bracket, okay, the number to be undefined? Okay, this is the second question. And then you guys, okay, very smart, okay, tell me it is not possible because in the orthogonal basis, we don't consider or we ignore, okay, any zero vector, right? Okay, so we don't have any product, okay, to dot itself, okay, to become zero vector, okay, because there exists no zero vector inside, okay, inside the orthogonal basis, right? Okay, so I hope you can see why I keep mentioning dot product return real number, and then okay, and so on and so forth, right? Okay, so I hope you can really understand, okay, why I keep mentioning that until here. All right. Okay, so by the way, let me remind you the whole idea of the theorem 6. Okay, suppose, okay, there is an orthogonal basis. Okay, it consists of n vectors, v1, v2, until the last guy, vn, for the general Rn space. And now I would like to see a random vector in the same Rn space, random vector, say vector u, okay, and I would like to see whether or not I can really express vector u in terms of the vector inside the orthogonal basis, or simply speaking, okay, whether or not I can express vector u in terms of the orthogonal basis. Okay, the answer is yes, and then I can write in this way. The vector u, okay, will be equal to, okay, a long expression, but actually I would say there are some patterns you can observe, and also you can see that, okay, suppose basically, okay, let me tell you, you can easily verify, okay, the result. Okay, for example, if you are going to consider, I forget to change the pen, okay. Okay, suppose you will want to check, okay, vector u dot v1, okay. So can you tell me what is the thing on the right hand side? If you are going to check the dot product, u dot v1, okay, actually quite a number of terms are gone because they are orthogonal to each other, right? Okay, so you see that. Okay, this guy, oh, sorry. But, okay, the rest of them will be equal to 0. Okay, since, okay, vi dot vj, they are orthogonal to each other, right? Okay, so whenever I doesn't equal to j, right? Oh, sorry, this is not better. So we don't need an arrow. Okay, because, okay, inside the orthogonal spaces, all vectors or any combination of vectors are orthogonal to each other, right? So the dot product of any two distinct vector will be zero, right? Okay, so you can see that, okay, when we are going to consider, okay, u dot v1, okay, so actually starting from the second term until the last guy, okay, all of them will be gone and equal to 0. And then you can see that, okay, these two terms can be cancelled out. Okay, so what you get is, I don't have enough space. Okay, I write here. Okay, so u dot v1, okay, simply equals v1 dot u. Oh. Right. Okay, so I hope you can simply verify the reliability, okay, reality of the theorem 6, okay, the reality, okay, or the truthfulness, okay, of the theorem 6, okay, by using this idea. Okay, so that's why, okay, I say, even though this formula, okay, may be a little bit long or a little bit complicated, but actually when you follow, okay, the pattern, okay, or if you examine, okay, it closely, actually it reduces us with a very direct or straightforward result. Okay, so don't worry about the difficulty or the complexity of this formula. Okay, now I would like to share with you, okay, the following example. Okay, I would like to borrow, okay, the information from the example 10, and in example 10, okay, we verified that, okay, the 4 vectors in a set, we call it to be a orthogonal basis, right? Okay, so now I would like to borrow that set, okay, and then I would like to express a random vector 1, 2, 3, 4, okay, in terms of this orthogonal basis given by the example 10. Okay, so to begin with, okay, so I simply assign a name for the vectors. Okay, but by the way, okay, those underlined vector shown in the example 10. Okay, so in the example 10, okay, so this is not a new stuff. Okay, but here, okay, please help me to correct some typos. So please change, okay, the circular bracket, okay, into angular bracket, okay, to represent the vector. All right. Okay, so for V3, okay, for V3, okay, we are having 1, 0, 1, 0. All right. All right. And then for V4, okay, we just replace it by the angular bracket again, okay, to make it precise. Okay. Now I would like to assume, okay, of course, no, don't forget, we also need to change the vector. I mean, the presentation, okay, for the vector u. Okay, so now I would like to, okay, use the idea about linear combination because theorem 6, yes, theorem 6 told us that, okay, we can always transform the given vector u in terms of the linear combination, right, of the vector in the orthogonal basis. Okay, so assume, okay, we assume vector u will take the following form. Okay, we'll take the following form. Okay, so you can see u1 equals alpha 1 times vector 1, or v1, plus alpha 2 times vector v2 plus alpha 3 times vector v3. And the last guy plus alpha 4 times vector v4. In particular, alpha 1, alpha 2, alpha 3, and alpha 4 are real numbers, are real constants. All right. Okay, so our job, okay, our job is to find out alpha 1 until alpha 4, right? Okay, so this is our target. So let me put it down. Okay, our target is to find all alpha 1, alpha 2, alpha 3, and alpha 4. All right. Okay. So I use another color. So for alpha 1, I may not be able to show the theorem 6 in the same screen, okay, because it will make it too small. Okay, so you can focus on the theorem 6, and in the meantime, okay, you can see the screen. Okay, I try to illustrate how we can use the formula, okay, to compute the different constant term. So after some simplification or some algebra, we get alpha 1 to be 4 divided by 3, alpha 2. You can follow something similar. Again, after some algebra, okay, some simplification, you get half for the alpha 2. Okay, so for alpha 3, alpha 4, I just put down the answer for you. Okay, so if you have time, okay, verify for me. Okay, later on. Okay, so our target is just shifted. Okay, alpha 1, alpha 2, alpha 3, and alpha 4. Okay, all of them are real numbers. Okay, so now the next job is to plug in those kind of constant term, alpha 1, alpha 2, alpha 4, alpha 3, and alpha 4. Okay, back into the linear combination, right? The expression for the linear combination. Okay, so we have vector u equals, of course, 1, 2, 3, 4. Okay, given by the question, can be written as 4 divided by 3 times the vector 1, which is 1, 2, 1, 0, plus, okay, half time the second vector, negative 1, 1, negative 1, 1. Okay, minus alpha 3 is negative 1. Oh, okay, maybe I put it this way. Okay, the last guy. All right, so, okay, by taking a look, the blue part, okay, the blue part. So I make use of the theorem 6, okay, then write down the given vector u, okay, to be the linear combination inside the vectors of a particular orthogonal basis. All right, so this is the way how we can make use of the theorem 6. Okay, so well done, guys. Okay, you are really with me. Okay. Okay, so maybe we take a break. Okay, seems that we already talk about an hour. Okay, so let's take a break, a 15 minutes break. So when we come back, okay, we will finish the last idea. Okay, the last idea of this material. Okay, so we will come back around 5:45. Okay, so see you guys. Okay, guys, so let's come back. Okay, so before the break, we finished the idea of film 6, right? And then we work on a simple example, okay, for the orthogonal basis, and then we want to express a random vector in the form of the linear combination of the vector, the orthogonal set. Okay, and now, okay, we have another question. Okay, we would like to address. Okay, so firstly, okay, so let's take a look. Okay, some description. Okay, so we may have an idea, have a question in mind actually. Okay, suppose you are given a basis, okay, whatever basis, okay, I don't know which kind of basis it is, okay, for the general Rn space. Okay, now I would like to ask whether or not I can, okay, transform this given basis to become an orthogonal basis. Okay, so this is my idea, okay, or this is my question. So let me repeat. Okay, suppose you are given a basis. Okay, given a basis. Okay, I don't know which kind of basis this is. Okay, I just want to know, can we change, okay, the given basis to become, okay, an orthogonal basis? Okay, of course, we build from the given basis. Okay, so actually this kind of question, okay, can be answered by the following process, which is called Gram-Schmidt orthogonalization process. Okay, but I'm lazy. Sometimes I simply call it Gram-Schmidt. Okay, Gram-Schmidt. Okay, so I'm lazy. Okay, so in case I just simply call Gram-Schmidt, okay, please refer to this one. Okay, to this process or to this part. Okay, so now I would like to develop this kind of idea. Okay, to see whether or not I can give some new insight. Okay, in this part. Okay, all right. So let's take a look at the theorem 7. Okay, theorem 7. So you may see, okay, actually it's share with you some similar findings, right? Okay, some dot product or a long expression. Okay, but anyway, okay, this is a process, okay, to help us to transform a given basis, okay, to become an orthogonal basis. Okay, so initially, suppose there is a given basis, okay, okay, in this basis, there are n vectors, okay, n vectors, W1, W2, until the last guy, Wn, all right? So this is the initial given information, okay, for the Rn space. And then after some process, okay, okay, and then finally, okay, you will get another set, okay, another set, okay, V1, V2 until the last guy Vn, all right, and then I will say, okay, this set, okay, will become an orthogonal basis, okay, will become an orthogonal basis for the general Rn space, okay, so this is the central focus of this part. Okay, so we would like to rely on the so-called Gram-Schmidt orthogonalization process, okay, to help us to transform a given basis into an orthogonal basis, okay, for the general Rn space. All right, so this is the idea. All right, but in the detail, okay, in the detail of the process, okay, actually, I would say, if you are interested in, okay, so you may go to borrow some book or to search online. Some authors, okay, or some books, okay, may want to use some geometrical idea, okay, to illustrate how you are going to get the following result. Okay, but of course, I would say, we may, it will take some time, okay, to develop such kind of idea. Okay, so maybe a little bit out of the scope of this course. Okay, so I simply leave it, okay, for you. Okay, so if you are interested in, okay, how to develop the following formula, okay, the following process, okay, go to the some textbook or go to some online reading material. Okay, you will see some geometrical idea, okay, or geometrical insights, okay, to help you to understand the idea. Okay, so I just want to tell you, okay, how we are going to play with the Gram-Schmidt process, okay, in order to convert the given basis to become an orthogonal basis. All right, so you can see quite a number of dot products over there, right? Okay, so I hope you can still remember, okay, the discussion before. Okay, so dot product, okay, we return it with real numbers, okay, real number divided by real number, okay, of course, another real number, okay, and so on and so forth. Okay, so let's move to the example 12. I would say it is also a long example. You can see the process, okay, for the process. Okay, so now let's consider a basis. Okay, consider a basis. Okay, for the R5 space, 5-dimensional space. So you can see for each vector, it consists of 5 elements. Okay, and in particular, okay, there are 5 vectors. Okay, so you at this moment, okay, you should be able to tell, okay, 5 linearly independent vector. Of course, it will become a basis, okay, for a particular R5 space. Okay, now I would like to, okay, convert, okay, or construct, okay, an orthogonal basis, okay, for the same R5 space by applying Gram-Schmidt process. Okay, so in particular, you can see that the given basis, okay, it is not an orthogonal basis. Okay, you can verify that. Okay, and so we would like to, okay, learn, or we would like to apply Gram-Schmidt, okay, to construct an orthogonal basis by, okay, this initially given basis. Okay, so for simplicity, okay, I may need to work out some initial setting, okay, or to name some vectors, okay, to begin with. So as usual, okay, we may use, or we may adopt, okay, something similar. Okay, for example, I use W1, W2 until the Wn, okay, to denote the vector in the initial given basis. Okay, so you can see W1, okay, I may use, okay, W1 to denote, okay, the first vector. Okay, I use a sharper color. Okay, so you can see W2, W3, W4, W5. Okay, so just follow the idea, okay, from the theorem 7. Okay, for the initial basis, okay, W1, W2 until the last guy, W5, so to be the vector inside the initial basis. I also put it down in the notes. Okay, you can see, okay, why we call it W1, W2. Okay, now I would like to apply theorem 7. Okay, theorem 7. Okay, but here, okay, before applying theorem 7, okay, I would like you guys to have some, to spend some time, okay, to observe something. Based on W1, W2, and W3, okay, can you have a look first? Okay, I would like you guys, okay, to tell me if we just consider W1, W2, and W3, can they form an orthogonal set? Please help me to verify. Okay. If we just consider, okay, let me repeat my question. If we consider W1, W2, and W3, can these 3 vectors already form an orthogonal set? Okay, I see some response. Very good. Okay, any other idea? Well done, guys. Very good. Well done. Okay, so to at least, okay, I can observe, okay, I'm very satisfied with your response so far. At least you can tell. Okay, at least you can still remember what is meant by orthogonal set, right? Okay, this is the first thing. I'm happy. And the second thing, okay, why I would like to call for your attention, okay, for these 3 vectors, W1, W2, and W3. Because, okay, when you get back to our target, we want to find out a set which is called orthogonal basis, right? So if we can single out some vector that are already in an orthogonal set, okay, so this is already a part of the orthogonal basis, right? Okay, so actually W1, W2, and W3 actually fall into this kind of category because, okay, W1, W2, W3, okay, forms, it's not formed, right? Okay, 3 vectors, English. Form an orthogonal set already, right? Okay, you guys help me to verify this. Well done, guys. Okay, so these 3 vectors already form an orthogonal set. So we just put them aside, okay? So we just ignore them. Okay, I don't need to work with them anymore because they are sufficient to be included in the orthogonal basis later on, okay? What concern most, okay, what is the troublemaker is the last 2 vectors, okay? These 2 vectors, okay, we may need to have some further analysis or processing, okay, in order to make the whole set or the whole given basis to be an orthogonal basis, right? Okay, so under this observation, okay, we don't need to bother about W1, W2, W3. So I simply assume, okay, V1, V2, V3. Okay, do remember, V1, V2, blah, 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 Vn. Okay, the decided vector in the last or in the final orthogonal basis. Okay, so I hope you can let, okay, the use of notation as in example 7, right? Okay, so you can see V1, V2 until the last guy Vn. Okay, we use this kind of notation to denote the vector inside the designated or decided orthogonal basis. Okay. Okay, so as mentioned, okay, from this statement, okay, we already know that W1, W2, W3 is all of them are qualified to be included in the designated or the final orthogonal basis, right? Okay, so we simply assign, okay, V1, V2, V3 equals W1, W2, W3. Okay, so they are qualified, okay, to be to put in the finalized, okay, orthogonal basis. Okay, and then now I would like to compute V4. Okay, I would like to compute V4. All right, so what are they? So when you are going to refer to the to the film 7, okay, for the Gram-Schmidt process, so W4, of course, you are going to put in the corresponding index, so you can see. Honestly, this is a big guy or complicated expression, but inside each individual one, okay, it follows some pattern. All right, you can check. Okay, you can compare the result. Okay, from film 7. Okay, but of course by changing the corresponding index. Okay, and now, okay, everything inside this expression can be obtained, right? Okay, so V1, V2, V3, W1. Okay, of course, no W1 is in the question. Okay, W4. Okay, you can see what is W4. Okay, because we already defined in the very beginning of this page. Okay, so I try to skip some intermediate steps. Okay, because I know you guys should be no problem to work it out later on. Okay, I just want to show you. So after some evaluation, okay, for the dot product or some simple algebra, so you get, okay, and then the last guy, 1/4 minus 10. Sorry, minus 0, not 10. Okay, all right. So after further simplification, okay, of course, this is big guy, right? This is also a big guy, okay. It takes time, okay, but I skip it, okay, to save some time, okay. After some evaluation on simple algebra, okay, we will get, okay, and vector 4, okay, V4, okay, to be, okay, is going to be included into the orthogonal basis, okay. Okay, so V4 is done. Okay, how about the last guy, V5? Okay, guys, V5. Okay, I will leave it for you. Okay, for the Gram-Schmidt process. Okay, and then I give you the answer directly. Okay, so you can treat it as a practice. Oh, sorry, this is not 7. 1 divided by 7. Okay, so for V5, after some steps, okay, you can write it out, and then you should be able to get the following vector. Okay, so now, okay, based on the old notation we introduced it in the film 7. Okay, so now it is time to report the required or the decided orthogonal basis. Okay, will consist of, okay, the following vector. Okay, the following vector. Okay, so let me put it down for you first. Okay, so basically, okay, we finish okay the transformation okay from a given basis of a R5 space into an orthogonal basis. Okay, and in this set, it consists of five vectors, and after some evaluation or after some observation, we can see that this basis okay can be claimed or can be verified to be an orthogonal basis. Okay, so I hope you guys at this moment can check. Okay, why I can claim this is orthogonal basis. What kind of condition they have satisfied it? Okay, for example, when you're going to consider any particular two vectors and then the dot product. Okay, so what you are going to get, and then yeah, actually I guess okay you can understand what I'm talking about. Okay, it also serves a practice. Okay, to review some learned material, right? Okay, so okay, this is the example 12 okay for this part. Okay, so far so good. And then before closing this topic, okay, I would like to end with one interesting terminology. Okay, I would like to share with you. Okay, so suppose you get an orthogonal basis. Okay, you get an orthogonal basis. Okay, initially, and then you find that every vector in this okay orthogonal basis has length equal to one. Okay, has length equal to one. We will call okay this basis this orthogonal basis to be orthonormal basis. Orthonormal basis. All right. Okay, so this condition only happen when okay all of the vectors with length equal to one. Okay, so if this is the case, we call the basis to be orthonormal basis. Okay, all right. Okay, so this is the last concluding remark. Okay, for the topic 4. Okay, so basically we are done for the topic 4. All right, for the topic 4, and then what remaining is the some practice question. So I hope you guys may try to play with them. Okay, if you have time. Okay, so basically, okay, we are done, and then on Wednesday we will start the new topic, topic 5. All right. Okay, so as usual, I'm going to show you all of the pages covered today. Okay, so, yes, this page. Okay, so for every page, it will last for 20 seconds again. Okay, we start from page 22. All right. So let's show all of the pages. Okay, we covered today. Okay, any particular page you want me to show again? Okay, so basically we get the topic 4 done. Okay, when we come back on Wednesday, so we will start the new topic, topic 5. All right. All right. 23. Okay, here you are. Okay. Is the size all right for you? A little bit larger, or is it okay? You're welcome. Okay, by the way, I will not teach anything new. Okay, so if you have no particular question, okay, you are free to go. See you guys. Bye bye. See you guys. Bye bye. You're welcome. You're welcome. All right, 28.